In our first lecture on conductivity, we thought about the conductivity of a metal from the point of view of Drude theory. And as I said last time, that theory goes back to 1900. It predates quantum mechanics. We treated the distribution of electrons with a Maxwell-Boltzmann distribution, which places no limits at all on how many electrons might be moving at a given speed. But we know that the behavior of electrons are inherently governed by quantum mechanics. So what happens if we try and bring quantum mechanics into the picture? In this lecture, we're going to do that. We're going to start with something called the free electron model, which does impose the rules of quantum mechanics, but basically treats the bonding in the most naive way possible. So the idea behind the free electron model is almost analogous to the particle in a box treatment that you see when you take physical chemistry. We're going to say that our crystal has a certain potential, which we're going to call V naught, when the electron is in the crystal. And the potential of the electron leaving the crystal, we're going to say is infinite. Right? So the electrons are trapped inside the crystal. All right, so what's our crystal orbital wave function? Remember, we talked about this back in chapter 6. The block function says that the wave function of a crystal orbital is equal to e to the eikx times the basis set u of x. Right? So let's work in one dimension because it's simpler. Now, in the free electron model, what we're going to do is to say that our basis set is just 1. Right? The fact that we said the potential anywhere inside the crystal is the same is more or less saying that we're going to ignore the fact that there's actually nuclei in the crystal that the electron might be attracted to. Right? So we're not thinking about atomic orbitals here. We're not thinking about any bonding whatsoever. We're just confining the electrons to be within the crystal. And if we do that, then the wave function reduces to e to the eikx. Now, if we were to use this wave function in the time-independent Schrödinger equation, you would get a solution that looks like this. E equals V naught plus h bar squared over 2me times k squared, right? Where k is the crystal momentum of the electron, right? K is the quantum number that we talked about in great detail back in chapter 6. If we were to plot the wave functions, which are solutions to the Schrödinger equation, we would see wave functions that look like this. Here, I've just taken something off the internet, which is the solutions to the particle in a box problem. But they're exactly analogous to what we would find when we solved the free electron model. Right? If we were to say k equals to 0, that means the wave function becomes 1. Right? Then we would just have a straight line from one end of the crystal to another. If we make k larger and larger, we get more oscillations in our wave function. And remember when we were talking about our hydrogen atom chain, and there we said that the wavelength of the wave function is 2 pi over k. So you can see that as k gets larger, the wavelengths get shorter. We get more and more squiggles in our wave functions. Now let's look at the energies of these wave functions as a function of k. So here's what our free electron model band structure looks like. We've got this expression here that relates the energy of any crystal orbital to its wave vector k. And you can see it's just going to be a parabola. And so the larger k, and is the more oscillations in our wave function from one end of the crystal to the other, the higher the energy. You might notice that where I did have the mass of an electron here, I've substituted the variable m star, which is the effective mass of the electron. And the effective mass, it's still a mass, but it's kind of like a fudge factor. So we don't have to stick with the fundamental constant mass of an electron. We can pick a slightly different value, and that value, as you can see, will dictate the width of our band. When m star is small, we have a steep band, a wide band. when m star is large, we would have a much more narrow band that doesn't rise and fall as steeply. Now let's compare our free electron model to the tight binding model we got when we looked at the band structure of an infinite chain of hydrogen atoms. The agreement is not so terrible given how simple our model is here. They're not the same. I mean, you can see that you have a flattening off of the wave function near the bottom and top of the bands in our tight binding model, which is completely absent in this parabolic band. And, of course, we did use some fudge factors. We picked the V naught and we picked the m star so that we could match the energy position of the bottom and the width. But in truth, the band structure of our hydrogen atom chain did have a minimum that was very loosely parabolic. But in the free electron model, we're going to treat it exactly as a parabola. That doesn't mean that the free electron model is going to capture the kind of features we're going to have when we start bringing in p and d orbitals, or when we have a unit cell that has multiple atoms in it, but at least it's a start. We can model the band structures of metals whose bands are largely based on overlap of s orbitals using this approach. Now let's dig a little bit deeper behind this m star, the effective mass. This is our expression for the energy of any crystal orbital in the band structure. If I were to take the second derivative of this function with respect to k, then the term on the right is just going to be reduced to h bar squared over m star. And then the term on the left is going to be the second derivative of the E versus K function with respect to K. What does this do for us? What it does for us is it relates the effective mass to the curvature of the band. So when the band is very wide, it has a big curvature, the second derivative of the E versus K function is going to be a pretty big number, and that means that our effective mass is going to be small. On the other hand, if our band is flat, right, so there's not much curvature to the band, then the second derivative of the E versus K function is going to give us a pretty small number. Small curvature leads to a small denominator, which leads to a large effective mass. Furthermore, we can relate the mobility to the effective mass. Right? Our expression for mobility was the charge of the electron times the relaxation time divided by its mass. And so if instead of using the mass of an electron, we use the effective mass, we can see that when the effective mass is small, the mobility is high. So remember, mobility is one of the key things that tells us about conductivity. And what this is telling us is that when we have wide bands with a lot of curvature, we're going to get a high mobility. And so that's going to lead to high conductivity. At least that's half of the equation. The other half of the equation is the concentration of electrons that can move in response to an applied electric field. And in the Drude model, we just assumed all the valence electrons could respond to the electric field. But that's not really the truth. What we have to think about is how much energy does it take to excite an electron from a filled crystal orbital to an empty crystal orbital. And that's where this function here given at the bottom, which is called the Fermi-Dirac distribution function, comes in. At 0 Kelvin, we said that all of the states below the Fermi level are fully occupied, and all of the states above the Fermi level are empty. All right, what happens when we're not at 0 Kelvin? Well, that implies that this is no longer exactly true, and that's what the Fermi-Dirac function gives us. So it basically smears out the occupation of the states around the Fermi level. So at a finite temperature, we find that there are some crystal orbitals above the Fermi level that are occupied, and below the Fermi level, there are some crystal orbitals that are empty. And that means that, let's say, an electron at a crystal orbital of this energy does have a chance to move into a crystal orbital that's empty. But a crystal orbital that's half an eV below the Fermi level, it's just too far for it to be thermally excited into an empty state. And as the temperature goes up and up, this function smears out more and more. Now, if we were to multiply this Fermi-Dirac function times the density of states in the free electron model, we would get a curve that looks like this. It turns out that the density of states in the free electron model increases as the square root of the energy. Why this is important is that it tells us a couple of things. First of all, it tells us that no, not all of the valence electrons can respond to an applied electric field. It's only this tiny fraction of electrons that are up here close to an empty state, right? So maybe it's only a few percent of the valence electrons are going to move when we apply an electric field. So that might tend to imply that the concentration of charge carriers that can reply to an external field might be the same from one substance to the other. But the thing that's different is as we add more electrons, the filling goes up, and that means that the density of states at the Fermi level gets larger. As the density of states at the Fermi level gets larger, even though there's only a few percent that might be able to respond to the applied field, that number gets larger. So that kind of helps to explain why potassium is a better conductor than rubidium and sodium is a better conductor than potassium, because as the density of the atoms gets higher, the filling of our free electron band goes up. Now, what about the speed of the electron? That's another parameter that's going to be important in figuring out the conductivity. In the Drude model, it was a Maxwell-Boltzmann distribution of speeds. In the free electron model, it's actually dependent upon k. So we know that the momentum of the electron is equal to h bar times k. It's reciprocal space wave vector. Then we can say that the momentum of an object is its mass times its velocity. So let's take the effective mass of the electron times its velocity equals h bar k. And then finally, we can solve for the velocity. And we see it's h bar k divided by m star. So the main takeaway point here is the velocity depends on the value of k. These electrons that are in states near k equals 0 have almost no velocity. At k equals 0, the velocity goes to 0. But as k gets larger and we move out here toward where the band filling stops, then the velocity is much higher. What is the velocity of those electrons that are at the Fermi level? Well, we can make an estimate of that. If we say that the energy is equal to 1/2 mv squared, right, that's the kinetic energy expression, and we take the energy to be the Fermi energy, then we call the velocity of those electrons the Fermi velocity. And we can solve for the Fermi velocity, and we get the square root of 2 times the Fermi energy divided by the effective mass. So what we can do is in the free electron model, depending on the density of the atoms, we can come up with the Fermi energy and then use that to estimate the velocity of the electrons at the Fermi level. So for copper, that estimate is 1.6 times 10 to the 6th meters per second. Remember, in the Drude model, we estimated the average speed of the electrons to be 1 times 10 to the 5th. So the electrons are actually moving much faster here, more than an order of magnitude faster. That is, at least the electrons near the Fermi level, which are the ones that count. And why do I say they're the ones that count? Well, let's imagine what would happen if I applied an electric field. So if we apply an electric field like this, so this end would be the positive end, this end the negative. The electrons that have negative k values, that would be traveling in the left-hand direction, they're going to be attracted to the positive charge. At the same time, the electrons that would be traveling to the right, now they're going toward a negative charge, and that's going to be repulsive. It's going to shift the distribution here in such a way that we have more electrons traveling in the negative direction than we have electrons traveling in the positive direction. And those uncompensated electrons, here I've really exaggerated that, but these electrons that I've kind of marked with the bracket, which don't have a corresponding electron traveling in the opposite direction to cancel them out. All right, so those uncompensated electrons are the ones that carry the electrical charge. And those uncompensated electrons are located around the Fermi energy. So it's the velocity of those electrons that really matters when we talk about the conductivity of the material. So what we see is, yes, the number of electrons that can move when we apply an external voltage is much smaller than in the Drude model. But the electrons that can move are moving much faster than they were in the Drude model. And so those two things kind of compensate for each other and allow us to get almost the same conductivity from both models. However, there are some really important differences. One of the things is the temperature dependence of metals. So here I'm plotting the temperature dependence of both aluminum and copper as a function of temperature. And what you see is that the resistivity goes down as we get colder. Put it another way, metals become more conducting as the temperature is lowered. For simple metals, that relationship is actually linear. In the Drude model, remember the electrons would slow down when we went to low temperature. And that certainly would lead to a decreased conductivity, not an increased conductivity. But that runs counter to the experimental observation here. What's happening is not that the electron speed is that different, or for that matter, that the number of electrons that can respond to an external field is very different. But what's different is at low temperatures, the atoms move around a lot more slowly. The thermal vibrations of the atoms is reduced, and the electrons then don't get scattered from the ion cores, if you want to think about it that way. And it's that reduced scattering from the vibrations of the atoms which makes the conductivity go up. And if we were to do some back-of-the-envelope kind of calculations about the density of electrons and things like that, we would see that in high-purity aluminum, at room temperature, the mean free path is about 29 nanometers. So not 3 nanometers, but 29 nanometers. So it's 10 times longer than our estimate of the Drude model. And at very cold temperatures, the electrons can travel almost a millimeter before they collide with an ion core. I mean, that's an incredible distance. Now, if we get to really cold temperatures, the conductivity kind of levels off and it becomes almost constant. And this conductivity here, where it stops changing with temperature, is called the residual resistivity. And where that comes from is actually from impurities in the metal. So the electrons are scattered by two different things as they try and move through the lattice in response to an external field. One would be atoms that are vibrating and therefore not in their proper place. And two would be defects and impurities in the crystal. So at very cold temperatures, the scattering from vibrating atoms becomes not very important, and it's dominated by the scattering of defects. And how cold you can get before this defect scattering dominates is really a measure of the quality of your crystals. So that's called the residual resistivity. Now finally, I think we're in a position where we can come back and talk about the conductivities of the transition metals. So just to kind of put things in perspective, we said that the conductivity at room temperature of sodium is about 2 times 10 to the 7th Siemens per meter. Magnesium is similar. Aluminum is about 4. If we look at the transition metals, we see that most of them have conductivities that are well below this. Certainly all of the early transition metals have conductivities pretty much below this, maybe with the exceptions of molybdenum and tungsten, which are comparable to magnesium and sodium. And then when we get over here to groups 8 and 9, we start also getting something pretty respectable. Goes down again when we get to group 10. But then when we get to group 11, the coinage metals, all of a sudden the conductivity jumps up by a factor of anywhere from 4 to 6. So what's going on here? What is responsible for that? Why is it that copper and silver are the kings of conductivity, and manganese and titanium and yttrium are terrible? Well, let's look at the band structure. So now we're kind of coming full circle. We talked about the Drude model, clearly too simplistic. We talked about the free electron model, and that's a little better. We're taking quantum mechanics into account, but no bonding whatsoever. So it's not going to tell us very much about one material versus another. But now let's see what happens when we think about the true band structure of a material. So here is the band structure for palladium, which has a face-centered cubic structure, a cubic close-packed structure. And what we see is as follows. There's a band here that's pretty wide. And if you use your imagination, you might imagine it going down to this minimum at gamma and then coming back up again. That's a band that has quite a bit of S character. So that's a little bit like our free electron band, if you will. Then down in this region, we have, if you count them up, 1, 2, 3, 4, 5 bands. And those bands are not nearly as dispersed and wide. And those bands, as we can see from our partial density of states plots, are the palladium 4D bands. Right? And then up here at very high energies, almost so high that it doesn't matter, are bands that have a lot of P character. So the key thing is that where the Fermi level is, you've got quite a few pretty flat bands that have this d orbital parentage. All right, what happens when we move to silver? That's one element to the right in the periodic table, one more valence electron. Well, the crystal structure of silver is also a cubic close-packed metal. It's got the same structure, but it has one more electron per atom. And what that does is it raises the Fermi level up. And now the Fermi level is not cutting through the d bands. The d bands are completely occupied, but it's cutting through this wide S-like band. And this band has a width that's, I don't know, maybe 12 electron volts, whereas some of these d bands have widths that are maybe 2 electron volts. And remember that wide bands lead to small effective masses, which lead to high mobilities. And so the whole key behind that periodic variation is once we get out of the d bands and we're filling up the s bands again, then the mobility becomes much higher, and that increased mobility is going to give us higher conductivity.